Hey everybody, this is Alex Merced and welcome to another episode of Catalogs, Manifests, and Metadata, oh my. And in this episode, we're going to keep delving sort of deeper into the Apache Iceberg story. So now we know what a data lakehouse is from the previous episode. The next step is to understand what a table format is in a little bit more depth. In the previous episode, we talked about how a table format is sort of like a metadata layer that allows engines to be able to recognize a table and scan it efficiently. But let's talk a little bit more about that, because there's three sort of major table formats in the data lakehouse space. That is Apache Iceberg, which will be a big focus of this particular podcast, Apache Hoodie, and Delta Lake. Now, they all try to solve the same problem in very, very different ways. Okay, but essentially the idea is essentially what they're doing is they're creating a bundle of metadata that when an engine, and first let's actually discuss what is metadata. The way to think about metadata is the data about the data. Okay, so it's not so basically, let's say I have a list, or let's take a look at my kitchen. I like to use this example. In my kitchen, I have forks, I have spoons, I have colanders, I have all sorts of different tools that I can use to do stuff in the kitchen. But I don't always remember where everything is. Now, I could just go look through the kitchen and open up every drawer and take a while to kind of find what I'm looking for. But what I could also do is I could create like a checkboard. I can get a checkboard with a piece of paper and make a list of here is the item and here's what drawer it's in. Okay. Now, I'm looking for a spoon. Okay. Again, I could go to the clipboard, which is not the kitchen. So I'm not actually looking through the actual thing. I'm looking through this external thing, okay, that gives me information to look through the actual thing more intelligently. So I can sit there and say, okay, a spoon is in drawer 3, and then I can just walk directly to drawer 3 and skip scanning the rest of the kitchen, okay? So you might also be thinking, well, that sounds a lot like an index. Well, oftentimes the metadata is very much working like an index in the terms of these formats, in the sense that they are an external structure, they are external data that allows you to scan the actual much larger data much quicker and efficiently. But how they do this is very different. So Apache Iceberg is going to do this through a 3-layer metadata tree made up of a metadata file that kind of tells you all the general concept of the table. So like, what's the table schema? What's the table's partitioning scheme? What is the snapshots of the table? You'd find that all in the metadata file. And the metadata file, from there you can discover which version of the table, because all of these table formats, they're generally going to have snapshot isolation, meaning every time the table changes, you still keep the metadata for the previous changes. So you'd be able to scan different snapshots, aka time travel, and scan how the table was in the past. So the way Iceberg does is it tracks different snapshots. In that metadata file, we can find the snapshot we want to scan, and each snapshot has a file called a manifest list. Now, it's a list of manifests. Before we go back to the manifest list, let's talk about what is a singular manifest. A singular manifest is essentially a group of files, and generally grouped together, particularly based on partition, but they're generally a group of files, and this manifest file lists these files along with metadata on these files, as far as what values they cover, how many nulls they have, all sorts of different metadata that can be used to figure out, hey, should I even scan that file in the first place? Now, there are generally many manifests for one table, so for that particular snapshot, there's a manifest list that lists those manifests, and actually contains the manifest level statistics. So instead of just the individual file statistics, it contains a manifest level statistic. So like, what are the range of values that manifest covers, and all those other stats for that manifest. Because there might be a manifest where none of the files make sense for my query. So using those manifest level stats, I can just sit there and say, I'm not going to scan that. And then there's the manifest. So any manifest we do scan, we can then figure out, hey, are there any files we don't need? And we can eliminate those. And then you end up with sort of the files you need to scan. So this 3 layers of metadata makes it possible for the engine to kind of easily whittle down the number of files it needs to scan to plan a very efficient query. And so that's essentially how Iceberg works. Okay, then there's Apache Hoodie. Now, Apache Hoodie works. It's probably the trickiest to initially understand of the three. There's a lot moving because it was built while Iceberg was created at Netflix, okay, by Ryan Blue and Daniel Weeks, basically dealing with sort of like a lot of the issues they had with an older technology called Apache Hive. Apache Hoodie was built at Uber, okay, dealing with sort of having to stream large amounts of data really quickly, constantly, okay. I mean, imagine how many Uber rides are going on at any moment. So the architecture is more sort of to sort of break up a lot of operations to be done asynchronously. So essentially the way Apache Hoodie works is that every transaction is assigned a timestamp. So essentially anytime something happens to a table, the way it is identified is by the timestamp that it happens, and only one transaction can sort of occupy any timestamp. So that's generally how you prevent two things from happening at the same time, because only one thing can claim any particular timestamp. So if something else does, then it has to find a different place in the sequence. So essentially what will happen is that it will claim a timestamp, and it'll create a little file called, timestamp dot requested, meaning, hey, I'm about to do this transaction, this thing's going to happen. And then it'll change that file to timestamp dot in flight, meaning I am currently doing the transaction, meaning it's currently writing the data files, and and depending on how you set up the table, there's copy on write tables, which you just rewrite the files every time. And then there's merge on read tables, where what happens is that instead of rewriting the files, it'll create these log files that then get applied to those files. I'll have a whole episode where I'll talk about merge on read and copy on write, because that applies to all three formats, have this sort of distinction, just in different ways. But essentially it'll do that, and then it has like another folder where it has a bunch of a metadata table that's used in the same way that the Apache Iceberg metadata is used to sort of skip files, and also has several other indexes to also assist in sort of skipping data files and identifying which data files to read. And essentially that's how Hoodie works. Essentially once the transaction is completed, that file becomes timestamp.committed with metadata on that transaction. So now then, while a table, an engine would first go to the metadata file in Apache Iceberg, in Apache Hoodie, it would identify the timestamp that it's scanning from, and then go to and basically rebuild the table based on the information within those timestamp transactions. And then the final format is Delta Lake. Delta Lake was created out of Databricks. So Databricks is a company that essentially provides managed Spark. So basically, a lot of people really enjoy using Apache Sparks, but like any open source software, you have to install it, you have to deploy computers to actually go run the software. So essentially, Databricks provided a sort of very, very integrated managed Spark solution. They've evolved from that sense, but I'm not going to get into that whole history. But in the process of doing that, they created their own format, so that way, to improve sort of that whole Apache Spark experience. And that is Delta Lake. And the way Delta Lake works, it's very similar to the way Git is. So if you ever used Git for like code, when you use Git, every commit is just, you're basically saying, hey, I've added these lines of code and I've subtracted these lines of code. And that's how you're able to track the changes to your code between different commits. So essentially that's how Delta Lake works. Every time you have a Delta log file, which are these JSON files, they track the files that have been added to the table and the files that have been subtracted from the table. So basically what you do to reconstruct the table at any point in time, you start from the first log file and go up all the way to the current, or based on the timestamp that you're querying, and you'll be able to reconstruct the table as it was during that time. Now imagine you have thousands and thousands of transactions that have occurred on this table. Well, that would mean thousands and thousands of log files. So that would get kind of slow iterating through those files and constructing the list of files for your query. So to deal with that, they have this other type of file called a checkpoint file, which is a Parquet file, which generally summarizes bundles of log files. So essentially, you might have 1,000 files and you're like, okay, well, to speed up querying the most recent snapshot, you might create a checkpoint of all previous snapshot, which summarizes the state of like all the log files in between. So that way you don't have to iterate through them. The checkpoint kind of summarizes the result. So there's those two types of files that are inside the metadata for Delta, and within those files also is summarized like partition, schema, things like that. So basically, always like the last log file is going to basically what you'll do is you start from the first one, and then you track the schema or the schema and the partitioning, and basically whatever the last one mentioned is what it is. So simple, but because of its particular design, it does preclude it from certain features that Apache Iceberg has, like partition evolution and hidden partitioning. But they deal, again, all three of these formats kind of come out at a lot of these things in different ways. So that's what table formats are. They're just, again, that metadata layer. So at the end of the day, like the same 1,000 Parquet files could have metadata written by all three formats and be read. It's still the same 1,000 Parquet files containing the same data. Okay, the only difference is whether a tool can understand any of these metadata formats, okay, in order to be able to read the table and understand which files should be read. So a lot of tools can understand Apache Iceberg, but I mean a good amount of tools understand all three. But definitely Apache Iceberg, for a variety of reasons we'll get into in future podcasts, has gotten very, very huge groundswell of sort of community support, not just within the open source community, but within the data vendor community, basically giving it a really strong amount of momentum at the moment. Mainly because it's open source and it's a community format, but also it's kind of in that sweet spot where it's not too complicated to understand, but it's not so simple that it precludes certain features, and it's not too tied to a particular vendor. So it provides sort of a really good format that people can kind of wrap their head around, take advantage of. People can build businesses around it without feeling that some other business can then, pull the rug from under them. And that's sort of, part of the reasons why it's gotten to where it is. Being adopted by so many different platforms. But with that, that's going to wrap up this episode on sort of what are data lakehouse table formats and sort of what's kind of going on in that space. And now we'll kind of get deeper and deeper into sort of how Apache Iceberg works. But I'll see you all in the next episode. Have a great day and enjoy. Keep listening to Catalogs, Manifests, and Metadata. Oh my! Tell your friends, subscribe, follow me on LinkedIn. I'll see you all later.